In this session on Geostatistics 240, we'll be looking at stochastic simulation, and particularly focusing on Gaussian type of simulation models. So I refer here to the MPS book. There's a good summary chapter there on Gaussian simulation or simulation using random functions. And then, of course, also the Equivalences book if you'd like to read some more detail about the theory. Okay, so why do we need simulation? So in the previous few sessions, we looked at kriging as a method for spatial interpolation. So here I have such an example. We have some data. Typically, we would calculate variogram, model variogram, and then would use that variogram in kriging to create a map of interpolated values. And in addition, we can get the kriging variance. So one thing we notice immediately is that this map is rather smooth, certainly compared to, say, for example, if I would reveal to you the actual reference data from which these 29 data are extracted, we notice this very smooth map. So why is that? Well, kriging is a regression model. So in regression models, we try to minimize the square variance, and the result of that, like any regression model, is that it is a smooth model. That also means that there are certain statistics in the smooth model that are not being reproduced, and that the data is much more varying than the smooth model, basically because it can be considered in many cases as a conditional expectation. So if we would calculate the variogram of this smooth map and the variogram of the data or variogram of the reference, we will notice two differences. The first is that the behavior at the origin will be very different because we have a smooth map, so we get this Gaussian type behavior. And secondly is that we get less variance. And indeed, if you calculate the variance of this map and compare it to the variance of the data, you'll see that that's quite different. So you say, why is that now relevant? Well, it's relevant in many applications. Certainly in applications, for example, where we're going to use our map for a certain purpose. For example, we'd like to use our map for building groundwater models for flow simulation. And so what matters in flow simulation is the spatial nature and heterogeneity of the hydraulic conductivity. And so if we use a smooth map, we'll get completely wrong predictions, for example, of the drawdown, if I would be pumping in a well, etc., or if I would be doing tracer injection, the tracer arrival times would be wrong. And in addition, I only get one answer, and so I would not be able to quantify uncertainty. So that is the limitation of spatial regression. Here's just another example of the same problem. So we have a very complex phenomenon. We extract limited amount of data and we do regression, and we get this map, which looks like there's almost very little resemblance to reality. So what is it that we'd like to achieve? So what we would like to achieve is not so much a least square type optimal map, means that the deviation between the map and the true map is as small as possible, but to have maps or a map that reflects certain statistics of reality. And the minimum amount of statistics that we can extract or should extract from some data is, first of all, it's the univariate distribution. And secondly, it will be the covariance function or variogram function. Since the covariance function and variogram function are already summary statistics of some bivariate distribution. So indeed, if I have this data and I calculate the histogram and I model the variogram, then what I'd like to have are maps that, first of all, interpolate still the data. So we'd like this idea of kriging to be maintained. But secondly, that these maps now also reproduce certain statistics, and particularly if I calculate the histogram of this map, it should be similar to this histogram. Calculate the variogram of this map should be very similar to this variogram. It's not going to be exactly the same, but it should be statistically similar. And so that would be the goal of stochastic simulation. The one thing you have to realize is that such map is not unique. I can create many maps that essentially have the same histogram and same variogram statistics. And so I'll no longer try to find a map that is as close as possible to the truth, but that reflects certain statistics of the truth. So here's the idea. We have some unknown reference truth. And from that we have limited sample data. So from that we can calculate variograms. Let's just focus here on that red and blue variogram. So, so imagine you have that red and blue variogram, could be a variogram model, could be an experimental variogram. What we'd like to do is create maps such that if I calculate the variogram on that map, you'll get a similar variogram as this variogram here. In addition, you also reproduce the histogram. So let's discuss a little bit some equivalences and differences with what you already know, which is univariate statistics. So in univariate statistics, we gather samples. For example, I could look at the weight of each person in the classroom. And what I do now ask is, if I get a new person, what is your best guess for the weight of that new person? Well, if you're thinking about least squares, then the best guess is the mean. That would be the best guess in the least square sense. So the best guess of a new sample would simply be this arithmetic average, and that will then simply be one answer. So if you say, well, I'd like to know an uncertainty distribution on the next person, then simply what you do is you can fit this model here, which just be fitting a distribution model with some parameters. So you can fit these parameters. And then in order to, we can then calculate directly probabilities or quantiles from this fitted distribution. But we can also say, well, we can also do Monte Carlo. So that means that we can represent the uncertainty on the weight of that next person simply by drawing many, many numbers and say, well, it could be any of these weights. And that would be then your answer in terms of an empirical distribution. In the spatial case, it's somewhat similar, but there are also differences. First of all, we get samples at spatial locations. So x1 to xn are spatial locations. And if I have now a new unobserved location where I have no observation and I'd like to make a best prediction, then I can use kriging. And so kriging is, again, one answer and gives you these weights in this particular linear model. So it gives weights to each of the points of the data. So now your question could be, well, what is the uncertainty in that particular location? And so then we would have to do the same as we do in the univariate case, which is to fit some specific form of distribution. And once we have that distribution, we can create many samples. Now, because we're in the spatial case, we have essentially many unknown locations. And so we would have to simulate all these locations together, which means creating samples at many locations. And that's what we showed in the case with Walker Lake, is that we can generate many images that are constrained to this data and reflect uncertainty. So the question you probably have now is, what are these distributions? And so the problem with this in reality is that there are very few analytical forms available as compared to, say, the univariate case. We have many forms available: local normal distribution, exponential distribution, etc. So now there are very few forms available, and in particular we'll mostly be focusing on the multivariate normal distribution. So more specifically, in spatial context or in a temporal context, we'll be now defining what's called a Gaussian process model. So earlier in the course, we already talked about one process model, which was the Poisson process model, Poisson point process model. So now a Gaussian process model, we'll be looking at a spatial process where we extend the notion of random variable, which say the random variable z, which was the univariate case, to now a variable z that's function of x. So one way of representing that is with a discrete grid. We say that we have a grid on which we have all the unknown, basically the unobserved locations. And so in that case, this process reduces to simply a multivariate problem. Maybe all these variables at those locations where we don't have observations become random variables. But that doesn't have to be the case. The process suggests that this could be just a continuous function of what's x, and the discrete grid is just a very special case. So in geostatistics, we often call this spatial process also a random function. And so that has to do simply with the function is now a random variable that's now a function of space or space-time. Fundamental to the Gaussian process is the multivariate normal distribution, and we discussed that earlier in the course, where the multivariate normal distribution is uniquely defined if I know the mean and I know the covariance between my various variables. And so this is then reflected in the covariance matrix, which is given over here. So this is just for the multivariate case. So what we'll do now for the spatial case is replace these x1 to xn with now z of x1 to xn. So we'll put in the unobserved locations as random variables in this. And so, but do mind that this could be an infinite set. But of course, in reality, when we executing this in computer programs, this will be a finite set. So once we specify the multivariate normal distributions, you can easily draw values from that multivariate distribution. So here's simply the case where the mean is 0. And so what we do to draw from the multivariate normal distribution is simply take the covariance matrix, do an LU decomposition. So you decompose it into a lower triangular and upper triangular matrix. And then you generate a set of Gaussian, independent Gaussian random deviates. So these have a standard normal distribution. You multiply that with this matrix, so you make linear combinations of those independent variables, which then gives you dependent variables. And a simple proof will show you that these x have the resulting x has covariance matrix C. So this is just drawing from the multivariate normal distribution. So imagine now that we are working on a grid with n grid cells, then this covariance matrix will be n by n. So let's do an example of that. So here's the simplest of simple examples where our covariance matrix is the identity matrix. So that means that there is no correlation. And we will be sampling on a 25 by 25 grid. So we have essentially 625 unknowns. Means the unknown is the value at each individual grid cell. And so my covariance matrix will be 625 by 625. So obviously, if I invert this matrix, it's simply the same as drawing independent values from the standard normal distribution at each of these locations. And that just gives you pure noise. So now imagine that I have a spatial covariance function specified. So for example, I've done some variogram modeling or covariance modeling, and I find that this is the model that I have, and it's isotropic. If that's the case, then we notice now that we're getting off-diagonal elements, and that makes sense, right? Because now I look at any two locations. So for example, the first two here, they have a distance of 1, and so for that distance of 1, I have a certain correlation, which is about 0.8. So that means at this off-diagonal here, that all distances 1 apart, I will get 0.8, and so on. Until I reach 3, then I get, again, 0. So if I invert this matrix, then doing that gives me, or do LU decomposition on that matrix gives me these samples. And so now I see that I have correlations that are starting to happen. So now let's look at this red one. If I increase the range, what you get is you get more off-diagonal elements. And so your your realizations of the multivariate normal distribution start now to show considerable correlation, which is due to the fact that I now enforce this correlation in my models, my samples. So this is as you know, this is already a very simple way of generating models that have a given covariance or variogram function. Now, if you have anisotropy, or you have nesting, or you have zonal anisotropy, it's exactly the same thing. You would just have to input into this covariance matrix just different values of the correlation in various directions. And so you have to just keep track of where you put those values, and it will no longer look like this. It will look somewhat different, of course. So that takes care of creating samples that have a certain variogram. But what about the histogram? So the problem here is that the Gaussian distribution, the multivariate normal distribution, has univariate distribution. It's also Gaussian. And so the problem is that the previous samples that we generated all have standard Gaussian distributions. Of course, in reality, we never have Gaussian distributions. And so the question is, if my distribution looks something like that, skew, how do I generate samples that have that distribution? So to do that, we simply rely on a simple method called the rank transformation. It's a transformation which is rank preserving, and that transforms any histogram into any other histogram. So here is a very simple example of how you transform data into a uniform histogram, or the uniform score transformation. So here we have original data, and the first thing we do always in a rank transformation is rank this data, and then we look at standardizing the ranks. We get this here, and so as a result, these v values now have a uniform distribution. So what that basically is, and that's the equivalent, is if you have any kind of distribution, whether empirical or theoretical, then you can simply transform the values of that distribution into uniform values by taking the CDF of that value. So that, in other words, the CDF of Z is a probability and therefore is uniformly distributed on the interval 0, 1. So that's kind of the inverse of Monte Carlo, right? In Monte Carlo, we give ourselves a V and we find using the quantile function what the value of Z is. So that's already nice. That also means that you can start to understand that I can now transform any distribution into other just by going via the uniform. So that is shown here. Here's just a theoretical explanation, but it's actually a very simple idea. I have, for example, a histogram of values. Imagine this is the empirical distribution. And I'd like to transform all these values into a new histogram, which is this histogram. So this is useful, for example, if my original values are normal score and when I want my new values to have a distribution like this. So the way it's done is very simple. You take your value Z, you map it onto the uniform distribution, then you take the uniform distribution and you map it back and you get a value of Y. And so you can do that for all Z and you get values of Y. So this is called rank preserving because if I have a value of Z here, then logically, because this type of distribution, because the CDF distribution is non-decreasing, I will find this Y here, which is on the left side, if there Z is on the left side of that Z. So that makes sense. So let's do that for this. Let's say this image is this, but I don't like this image. I like it to have a uniform distribution. So then I can just use the previous method and create a uniform score transformation. So here we see then the result. So this is the histogram of this new transformed data. And so what I have is a uniform distribution. But you also notice here that I have the spike at the origin. So why is that? Well, our rank transformation does require, at least in terms of creating a new histogram, that we don't have ties. So for example, in this particular case, I have a whole valley here where the elevation is exactly the same. So that means that all these values are transformed into the same value, which in this case is 0. So these ties can be broken, and so they will remain as ties. So basically, I have a mixture distribution now, which is the distribution with a bunch of zeros and then all the rest, which is then now this uniform distribution. So this could be useful for many applications, for example, for any kind of least square application, in particular, for example, calculating variograms, which are highly affected by high values. So variograms don't work necessarily very well with very skewed distributions. And therefore, taking uniform score transformation makes it a whole lot more easier to do because it just removes all the extreme values. Of course, then you have to be mindful interpreting the variogram because that will be the variogram of the uniform score transform. Well, in what we typically see is that ranges and types and so on, they're not that much affected by these transformations. So how is this practically done in SGEMS? And I will come back to that in the YouTube video on conditional simulation. So in SGEMS, for example, we specify our data, which, for example, in the drill hole case, the copper case, we had some great data. And so, for example, if I generate now a model of the copper deposit, I'd like it to have some similar histogram as the histogram of my data. So imagine here I have some copper percentages. And so what I'd like to have is histograms that look like this. And so for doing that, I have to first model, in order for me to make transformation, for example, transforming the Gaussian deviates into these values, I'll have to model the histogram first. And so we want to avoid any kind of parametric modeling because that remains limiting. So in SGEMS, we do a very simple non-parametric fitting here, where we take the 6 values and we make an empirical distribution by taking steps of 1/7. What that does is that it leaves me a little bit of space here because, of course, the value 20.6 is not the highest value that I can ever reach in this copper deposit. It's just the highest value in my data. So I'd like to extrapolate here. And so the way SGEMS does that is essentially it does these piecewise linear interpolations. And then you also have to specify the smallest value and the largest value you can expect. And so in SGEMS, those are specified over here. So this is the smallest value and the largest value. And of course, then we can also debate a little bit about how this extrapolation works. Is it linear? Is it more hyperbolic, parabolic? And SGEMS has some really good suggestions there, and I suggest not to alter these. For most of our distributions, we have skewed distributions to the right, and then these settings are quite adequate. Okay, so now I've shown essentially that I can create models that have certain variograms, certain histogram, but of course I'd also like to produce the information that's there. And that was really nice about kriging, is that at those locations it will interpolate that data. So I'd like to do the same. I'd like to create maps that reflect this information. For example, here I see that I have this red, so I should have more red in this corner. Here I have a lot of blue, so that means I have more blue in this area. So I need to be able to do that to account for this information. Okay, so how does that work? Well, we already have an idea of how to interpolate. That was our kriging. And we have now an idea of how to create models that have certain variogram and histogram. So that also means that if I take the first idea, namely do what's called unconditional simulation, so that looks all great in terms of variogram and histogram, but at the location of the data you make an error. So the idea in part 2 is that in kriging we don't make an error at the location, at those locations, but we have a problem with the reproduction of the statistics. So what we would like to do is use kriging to correct essentially the error you make in the unconditional simulation in terms of reproducing the data. And so the assumption here is that that error can be interpolated with kriging again. And so the theory shows that indeed if you do that, then you'll find conditional realizations that have the same histogram and variogram. We'll not be talking about the theory essentially of why that is. It's actually not that difficult of a development, but just tell you a little bit about how that works. So the way that works is we say I have a conditional simulation. So I write it as kriging, but kriging has not enough variance. We saw that when we calculated the variogram on the kriging map, it doesn't have a variance. So we'd like to add some variance to that. And so that variance is over here. So we're going to essentially estimate or simulate that error and add them to the kriging map such that we have essentially now a conditional simulation. So here is essentially how that is simply done. It's just a different notation here, but bear with me here. That again, that's the z of x, now it's called x of s. So basically what we have is we have some data, which is these stars here. Let me put on my pointer. We have these data, which are these stars here. And so if I do kriging, I calculate the variogram, do kriging, I get a nice interpolation that interpolates my data exactly. Then I do an unconditional simulation, and the unconditional simulation has the kind of variance I want. I see these fluctuations are much larger than kriging, but and it reflects the covariance, the variogram, but the problem is that it doesn't fit the data. So what I will do is simply calculate the error that I make in the unconditional simulation. So that's this error here. So you need here have a negative error, positive, positive, and negative error, and simply what I do is interpolate now the error. So I do a second kriging, and then I add up this error to this unconditional simulation. And of course, what that does is at the data locations now you'll find essentially no error, but you will maintain the properties of that of this red curve. That means that it will maintain the standard normal distribution and it will maintain the covariance, and that's to do because the error is interpolated with kriging. Again, that's a theoretical result that you can find in the literature. So this is just simply the way to do it. You krig, you create unconditional simulation, you calculate the difference, you interpolate this error, and then you just add everything up. Okay, let's talk a little bit about this data. And so in the literature, you'll find many names for this kind of data, which is point data or hard data. So remember that the random function is not defined on a grid, but of course, in reality, we'll have to go and simulate everything on a grid. And so then there are certain complications that happen, and particularly, we have to be mindful about what it is that we're simulating, namely the volume, which is also called support in geostatistics, and the definition of the grid. So the reason for that is a little bit, it's very confusing in the sense that your sample could have a very, very small volume. For example, you could go in the field and take a bucket of soil, analyze that, and that bucket of soil is mapped in an area, say, of 10 kilometers by 10 kilometers. So then when you generate models, you're not going to create models with billions of cells at the size of the bucket of soil. You will just do that at a much sparser grid. But when we make essentially the map at the end, whether it's a kriging map or a simulation map, the pixel plot essentially upscales these individual simulations to a larger grid cell, which could be easily, say, 100 meters by 100 meters. And so that's not really what's happening in geostatistics. And so I'd like to spend a little bit more time in explaining that because it's a standard confusion. So what I'm getting at here is that if you're going to simulate or estimate, you have to define a grid. And a grid basically means that you have to define a mesh which says that my sample, the values I'd like to simulate or estimate are on a certain distance from each other. So it should be dy here, but also that they have a certain volume. For example, if I use this square here, calculate the volume of that square or the area of that square. But I can also take a different volume over here. I can take a circle if I want to, an ellipse. And one of the requirements is that all these volumes and these shapes are exactly the same. It means they're all centered around this location. So I don't have, if I have a bucket, you can imagine that this would be a circle instead of a square. And so basically I have buckets at each individual grid point that maybe, these buckets may be very small, but the distance between the buckets may be very large. So then I have obtained data. So I have buckets that I sampled over here, over there. And so these are called hard data. Why? Because they are the same size of this, essentially this information. You also notice that this data does not have to lie on the grid. And so, for example, here's the data that lies exactly at the location. Of course, that will never happen in reality, or rarely happens unless you use a very dense grid. So most of your data lies off the grid, and so in that case, it's not a problem because in kriging, the only thing we need to know is the distance between the unknown and the data location, and so that's all obtained from the variogram, which, as you know, is a smoothly interpolated function. So the takeaway here is that random functions are just functions, continuous functions of x, but the computer implementations have discrete implementations, and so we have to be mindful not to just, if this value becomes, say, 5, what we do is when we make a pixel plot is we take this entire zone here and we call it 5. So it's kind of like we do an implicit upscaling, and that's not really there. So do be mindful when you do creation, when you create simulation and kriging, that you are mindful of the fact that you are simulating or kriging very small volumes. And that's why we call this sometimes point data or hard data, in the sense that it doesn't have an error. But then again, this idea of hard data, it's a bit of a misnomer, simply because it doesn't really exist in reality. So the interesting idea is actually that this conditioning with kriging it's a nice way to start thinking about stochastic simulation. I like it like that because it shows you the nature of stochastic simulation, that we'd like to impart certain properties on these stochastic models, namely that they reproduce certain statistics, but also that they reproduce some data. In reality, however, this kind of conditioning with kriging is rarely used. One of the reasons is that theoretically you will have to use global simple kriging. The second one, of course, is that you have to do this LU decomposition, which has some computational issues when you go to larger grids, say a billion cell grid. You can imagine doing that. And also, we'd like to work on more local problems, and so the global simple kriging is not going to cut it for us. Then secondly is that this LU decomposition will only simulate Gaussian processes. And so later in the course, we'll see that there are some significant shortcomings of these processes, that they can't model more, say, organized materials, particularly in geology. That is something we often notice, is that the world is simply not Gaussian. So we'd like to extend on that. I won't be doing that now. What I'll be doing now is looking at some alternative method for simulating the Gaussian process. And that method can then be extended to other non-Gaussian processes. So the method is called sequential simulation. And simply because what we rely on is we'll rely on the decomposition of the multivariate distribution, because after all, our grid is a set of unobserved locations that are unknown, so it's a multivariate distribution just as before. But we can decompose this multivariate distribution into a series of individual distributions. And that's shown here, namely the multivariate distribution can be written as, for example, let's put on the pointer. The multivariate distribution can be written as the probability of the first one, and then the probability of the first one given the second one given the first one, and so on down the chain. And the end one is the probability of the last one given all the previous one. So this is general. So this could be just random variables, could be a discrete random variables, or it could be again, just as before, it could be unobserved locations, variables at unobserved locations, and so then we have essentially a spatial problem. So this decomposition is completely general. The order by which you do this composition does not matter. In other words, I can write that for another order and it'll be exactly the same result. So then to jointly simulate all these events, it becomes now a matter of simulating from univariate distributions, and that's something we know very well. So you simulate A from P of A1 from P of A. Then once you have that value, so now we have a simulated value, you calculate, which would be the value A1 here. You calculate the conditional, or estimate the conditional distribution of A2 given this, and you simulate from that. Now you have two values, A1 and A2. You calculate the conditional distribution of A3 given these two, and so on. And you get at the end, you simulate from this big one. And so you end up essentially having a simulation from that multivariate distribution. Okay, so now you'll guess probably that we're going to apply this to the multivariate Gaussian distribution. That's correct. So here we have again the multivariate Gaussian distribution. And so some important properties that we'll be using is that any subset, if I look at any subset of these random variables, it's still a multivariate Gaussian distribution. It also means that if I want to condition any set on any other set, or any subset on any other subset, for example, I want to know x1 given all the rest, that is again a multivariate Gaussian distribution. Of course, the mean and the covariance will change, but the form of the distribution does not change. Also very important is indeed, if I look at a univariate distribution, conditional distribution, for example, f of x1 given the rest, then I have a conditional mean would be then expected value of x1 given the rest, or it could be for any xn. And what's really nice is that that's simply a linear combination of these conditioning values. So now you start to see, okay, I've seen that before, and indeed, this is linear regression, right? So this says that my conditional expectation is a linear combination of my data values. And so we'll see in the next slide that we'll be using kriging to determine these weights. So, okay, so here we have some more properties, and particularly, we'd like to estimate the conditional distribution of a Gaussian process. So remember that, imagine that I would like to estimate something at an unobserved location, and I have some observations. So what that essentially, if I would like now to look at the conditional distribution, then essentially what I'm asking is, what's the conditional distribution of f of this value given these values? So what we'll be assuming is that the joint distribution of all these is multivariate Gaussian. That also means that the conditional distribution of this given these is univariate Gaussian and have a certain mean and certain variance. So let's again look at the multivariate distribution of this. Well, what it has a certain covariance matrix. Remember that the multivariate distribution has a certain covariance matrix. Assume for now that the mean is 0. Then that multivariate distribution is uniquely defined by the covariance matrix, and the covariance matrix is written over here. So we notice here we have a number of parts in this covariance matrix. The first is the covariance between any two data locations. So this is of size n times n. That's the same as the covariance matrix that we've seen before. Then we have also the covariance between these values and the unknown. So that's this k here. And then we have the variance of your predictions of the location to be directives, for example, could be standard Gaussian. Then this variance here would be simply 1. If that is the case, then I can now, and as is shown, it's an easy proof. you can show that the conditional mean and the conditional variance can be written in this form. So you have this matrix K, etc. And so what we know, this should be a Z here, not an X. And so what we notice is that this form, and this form is something that you've seen before, namely that is simply the answer of simple kriging. Remember, you have to invert the covariance matrix and multiply that with this value of K to get the weights in the system, multiply that with the outcomes, namely the values of C. And so here we have the conditional variance. That was simply our kriging variance. Remember, this was the variance minus a part that belonged to the kriging variance. Okay, so now let's put everything together. So we saw two things about the sequential simulation. We saw that we can write a multivariate distribution as a product of a univariate conditional distribution. Then secondly, when we assume that the multivariate Gaussian distribution is a Gaussian, if the multivariate distribution is a Gaussian or a Gaussian process, then we know that every single conditional distribution is a Gaussian distribution. And we also know that the conditional mean is obtained using kriging, and the conditional variance is the kriging variance. So how does then unconditional simulation work in practice? And that's called sequential Gaussian simulation. Some people call it SGS, and other people call it SGSim. So in SGEM, it's called SGSim. And here we first talk about the unconditional form. So this form is exactly equivalent to this LU decomposition. So what we're doing here is we sample first from an unconditional. The first value we sample could just be the first value in the grid, so the bottom left corner of the grid, let's say. And remember that the order does not matter. And so we sample a value, we get some kind of value, say -2. So then we would like to estimate using simple kriging. We have now the second one, say that the value to the left of it. We estimate the conditional mean, which is obtained with kriging, and the conditional variance, and we draw that value from a normal distribution, which is now no longer standard Gaussian, but has a mean, which is the simple kriging mean, and a variance, which is the kriging variance. And so on. So we go and we repeat this kriging. So what it does is you have to repeat this kriging every time. And so this kriging system becomes bigger and bigger and bigger. And so, so that's what we get. So the order does not matter as long as we use all of the previous simulated values. And you say, yeah, but that doesn't solve my problem, because my problem before was essentially that I had a big grid, and so you had a bigger covariance matrix. So the covariance matrix is essentially growing with every single value that I simulate. Before answering that, how we address that issue, let's first look at when we have observations. So in that case, it doesn't change. It's just that in the first step, we no longer draw from the univariate Gaussian, but we already constrain to the observations that we have. So we just do, the first one is just the kriging estimate. We get a conditional expectation, we get a conditional variance, and we draw from this distribution, and then we go on. So as I said, in reality, we're not going to do it that way. First of all, it will not be any better than the conditioning with kriging. And secondly, we're going to use, just as with kriging, a limited search neighborhood. The advantage of that is that limited search neighborhood will allow me to do other forms of kriging, for example, ordinary kriging or kriging with limited search neighborhood. And we saw in kriging that has many advantages. And secondly, it will mitigate the problem of the computational issue. However, if you use a limited search neighborhood, then you're no longer having this this conditional decomposition, or this sequential decomposition is no longer fully valid. It now becomes an approximation because the decomposition that I had required that I condition to all of the previously simulated value. So the way that is mitigated in practice is that we don't use sort of a deterministic path or a constant path, but for each simulation we choose a different path. In other words, we choose a different where to start, what's the next one, and so on. So we no longer always start with the same one and follow a deterministic path. And so that is then a random path that changes for each new simulation. And so now we can also start replacing simple kriging by any other form of kriging, such as universal kriging, ordinary kriging, etc. So here's a simple example, and we'll talk more about that in the SGEMS tutorial on SGSim. So a non-known reference truth, we have some data extracted from it. We may have some external drift. So I can do universal kriging. So now I do sequential Gaussian simulation, which means that I visit a location, I search locally the neighborhood, I do a universal kriging at that location, then I have a kriging mean and a kriging variance, and then instead of putting the kriging estimate there, now I construct a Gaussian distribution with that mean and variance, and I draw from it. And then I move to another point until the grid is entirely full, and then I have a single simulation. To get another simulation, you repeat the exact same way, except you start somewhere else, and then you have a different random path, which gives you different simulations. So that's now sequential Gaussian simulation, and that already has a lot of practical applications, simply because now, as you can notice, you are reproducing a lot of interesting things. You're producing a drift or a trend, you're producing conditioning to data, you're producing the variogram and the histogram, and so these have really nice properties that you can put in flow simulators or other kind of applications and start quantifying the impact of these applications in terms of spatial uncertainty.